Let's now talk about how you can use the Rydberg equation to calculate ionization energy for different species. So first of all, what is ionization energy? This is the energy that's required to remove the electron. Let's first start with a conceptual problem. I want you to predict what the sign will be for the change in energy if you were to ionize an element. Is delta E positive, negative, or equal to 0? All right, having given you some time to think about this, let's talk about the answer and why it is what it is. So remember that, let's say we're talking about the hydrogen atom here. At the nucleus, we have a proton which has positive charge, and then the electron has negative charge. Opposites attract, and so they want to be as close to one another as possible. In order for you to remove the electron, you have to pull apart these dissimilar charges, right? They want to be together. In order to pull them apart, you'd have to add energy to rip them apart from one another, to pull the electron off. And therefore, because you have to add energy, the sign of delta E will be positive. The electron has to absorb light in order to get ionized. Now let's take a look at a calculation-based problem. So in this problem, we're asked to calculate what's known as the ground state ionization energy for the one electron species He+. So first and foremost, we recognize that He+ is a one electron species because helium has 2 protons. If it were neutral, it would have 2 electrons, but one has been removed to make He+, right? So this is a one electron species, and as a result, the Rydberg equation applies. We would use the delta E equals minus 2.18 times 10 to the minus 18 joules times Z squared over N final squared minus Z squared over N initial squared. Now we have to figure out what some of these variables are here. The goal of the problem is to calculate what delta E is. But we have a lot of other variables that have to be determined in order to solve it. And so first and foremost, let's talk about Z. So we said that for He+, we have a one electron species. The value of Z, however, tells you the number of protons. So Z for helium is equal to 2, right? It's 2 protons, atomic number 2. Always make sure to use the number of protons as the value of Z in the Rydberg equation. Additionally, we have to figure out what N final and N initial are in this equation. So the phrase ground state ionization energy helps us to determine that. When it says ground state, what that means is that the electron is starting in the lowest energy level. For a one electron species, what is the lowest allowed energy level? It's the N equals 1 level, right? So think of like the ground state as being like the ground floor of a building. The ground state for a one electron species will be 1. That's where it starts, is in the N equals 1 energy level. Now, what about the phrase ionization energy? That's going to tell us information about the final energy level. When you're ionizing something, you are removing the electron. Another way of saying that is you're going to move the electron very, very far away from the nucleus. And that gives us some indication for what we're going to pick as the final energy level, because the higher the value of N, the further you're moving the electron from the nucleus. We want to move it as far as possible from the nucleus, and so we want to pick a very big number for N final. Think of the biggest number that you can imagine, and hopefully what you come up with is infinity. That's the largest value of N that can be taken, and when you choose an N final of infinity, you're moving the electron an infinite distance away from the nucleus, which is another way of saying you are removing the electron, or you're doing an ionization. So ionization means that you're removing the electron, and whenever you see ionization, you're going to a final energy state of infinity. Okay, with all of that in mind, let's now plug in the numbers that we've assigned here. So the value of delta E for this ionization process is negative 2.18 times 10 to the minus 18 joules times, we said that Z is 2 squared over the final level, which is infinity squared, minus the Z squared, so again 2 squared, over the initial level, which is initially the ground state, initially N equals 1 squared. Now let's take a look at this equation. When we have 2 squared over infinity squared, when you divide by infinity, what happens to the number? It just goes to 0, right? The bigger you make the denominator, the smaller the value gets. So if you divide by infinity, that's going to make this value infinitesimally small. So that's going to 0. And that will simplify things down somewhat for us. So we're going to end up with negative 2.18 times 10 to the minus 18 joules times negative 2 squared over 1 squared. All right, so the delta E for this process is therefore going to be, notice that we have negative and then a negative here, right? So this negative and this negative wipe out, giving you a positive delta E, just like we predicted in the conceptual problem that you saw on the previous slide. And so what we have is 2.18 times 10 to the minus 18 times 2 squared, so that's times 4, comes out to 8.72 times 10 to the minus 18 joules. And that's how much energy would be needed to remove the electron in the one electron species He+. You can calculate that using the Rydberg equation. Now, if you really wanted to, you can convert this into a wavelength to find what wavelength of light is needed to ionize He+. And if you did convert this to wavelength using E equals hc over lambda, what you would find is that the wavelength of light would come out to 23 nanometers. This wavelength of light is in the ultraviolet region of the spectrum. So you would not be able to see this light, but it has a lot of really important consequences for us that UV light is capable of performing ionization. Now let's talk about the consequences of our determination here that ultraviolet light is capable of performing ionization. There are some benefits to this. So one benefit is that ultraviolet light can be used for performing photochemical reactions. Some chemical reactions require UV light to perform an ionization step, and so that has some beneficial consequences. But it also has some negative consequences. As you know, from your life experience, if you were to stand outside on a really sunny day for like 8 hours and expose yourself to a ton of UV light from the sun, you'll probably get a sunburn. And the reason why sunlight is harmful is because the ultraviolet light in sun can cause cellular damage. When your skin absorbs the ultraviolet light, ionization processes can occur. And one place where that could happen might be in the molecules that make up DNA. And when you remove an electron from DNA, you're oxidizing it, and it wants to get that electron back, and so it might participate in a chemical reaction to get the electron back. These chemical reactions can cause changes to DNA, which we know as mutations. And if you get enough mutations or enough of the wrong kind of mutations, then you end up with cancer, which is a really, really bad outcome and a negative consequence of the use of ultraviolet light. So it's important, I think, to understand the phenomenon, to understand that UV light has some beneficial consequences, right? Because it can be used to perform important photochemical reactions, but it also has some harmful consequences as a result of it being ionizing radiation. And so you have to make sure that you're applying it in the right environment under the right circumstances, and that if, for instance, you're going to be out in the sun for a really long time, that you take appropriate precaution in order to mitigate the negative consequences. All right, now the Bohr model was an amazing discovery, and Niels Bohr ended up being awarded the Nobel Prize for his work on this. However, there are some drawbacks and shortcomings to it that we're going to have to work on correcting. Here are some of them. One issue is that the Bohr model only works for one electron species, and so you could deal with hydrogen and describe its spectrum perfectly, and you can understand why hydrogen has a line spectrum, and find out what all the wavelengths of all the lines are exactly from the equation that Niels Bohr came up with. But you couldn't use it to describe a neutral helium atom. Sure, you can use it to do He+, but how often do you find helium in the +1 oxidation state, right? Helium is a noble gas, and so usually it's electrically neutral. So this is a problem. Other elements on the periodic table, right? Let's say that you're talking about lead. So lead is atomic number 82. It has 82 electrons normally, so you wouldn't be able to describe that. The only way that you would be able to describe lead would be if you were to prepare it in its +81 oxidation state, right? You'd have to remove 81 electrons in order to make this a one electron species. And you will never see lead with a +81 charge. That's not going to exist as a one electron species. And so this is going to exclude a lot of the elements on the periodic table. That's a big problem for us. Additionally, as you'll see when we get to chapter 13, it takes 2 electrons to make a chemical bond. And because the Bohr model only works for one electron species, it cannot be used to explain chemical bonding. And one more drawback of the Bohr model is that the Bohr model treated the electron exclusively as if it behaved as a particle. And as we discussed earlier when we looked at the de Broglie wavelength of the electron, its de Broglie wavelength is similar to its particle size, and so we must take into account both the wave and particle-like properties of electrons. You can't just assume the electron acts only as a particle. You have to take the wave-like characteristics into account. And so, although the Bohr model is really useful for the hydrogen atom, we need to make some modifications to the model so that we can better describe other atoms, ions, and molecules. And that's what we're going to talk about in the next section.